Welcome everybody. Today's lesson is all about electrophilic addition. The real definition of this type of reaction, it describes when two molecules react with each other, one of them as alkene and one of them as electrophile. But if it's the first time that you hear about electrophile, there is a beautiful definition for this thing here, which indicates to a species that is attracted to the region of high electron density. And since we're describing reactions of alkenes, we are talking about the presence of the double bond. And that's why we can consider the double bond area as a high electron density. So what are the types of electrophilic additions? What are the examples and how does it work? So stay tuned, guys. So let's start with the first case in which we're adding Br2 to an alkene. If you look at the Br2 as a nonpolar molecule like Br2, like here, just notice that the difference in electronegativity is zero, and that's why you are supposed to have a nonpolar molecule. But how does it work as an electrophile? How it's attracted to the electron density region? The reason behind because the orientation of the molecule of Br2 as it approaches to the double bond right here. The story says as we have electrons inside the bromine molecule, the electrons will start to repel each other from here. Like we have electrons in the double bond, electrons in the Br2. So these electrons will repel each other. This causes the electrons in the bromine molecule to flee to the side of the other bromine atom, causing this area to be partially negative area. And as a result of this process, the bromine, which is the first one, becomes partially positive. This process prone the double bond to be attacked by an electrophile, which is Br2. What does this arrow represent? Just keep in mind, it means that one of these carbons will be bonded to the bromine atom. So there will be a heterolytic fission. All of the electrons in the covalent bond will be going to the other bromine atom, causing a bromide ions. So what happened after that? Just keep in mind, the bromine atom is bonded to either this carbon or this carbon. So it doesn't matter here since we have Br2, there's no difference. Okay, so we will end up with a molecule like this. Suppose that the bromine atom is bonded to the first carbon, so we have Br right here. All right, and we have CH3 and other H. Just keep in mind, as we have a carbon atom with 3 bonds, we're supposed to have a positive charge on the carbon. All right, since we have this carbon in here and the bromine atom, which looks like this, we have 3, 4 lone pairs with a negative sign. So what happened? You will see that the positive sign here on the carbocation will be attacked by the bromide ion, and you have to draw an arrow, a curly arrow from the lone pair. So we have a lone pair right here. We have to just write this or draw this arrow, and we will end up with the same molecule. Okay, right here. Okay, we have CH3, and we have H. We have another H. We have H, and here we have Br, and down below we have another Br atom. So we'll end up with a di-substituted dibromo compound. And if you want to name this compound, generally speaking, we're just, we find the longest chain that includes the halogen. So here we have the longest chain, you can see it. So it's made of propane. We can start count with respect to the closest number of branches or halogens. So we have 1, 2, and 3. So we can say the compound is 1, 2 dibromo-propane. We mentioned a concept of carbocation, and now let's explain more details about this definition. Just keep in mind, the carbocation, it represents a positive ion, and in which the positive charge locates on the carbon atom. So how do we find this? What does it mean of that? So as we learned that in some of electrophilic reactions, we could have a carbon atom that is bonded to 3 bonds. And since it's bonded to 3 bonds, we're supposed to have a positive charge. So we have 3 types of carbocations, and they're different in their stabilities. So in this case, we're supposed to represent the alkyl group in which we have R. So R represents an alkyl group, and the alkyl group represents, like you could have CH3, you could have, let's say, hydrocarbon compounds. So we could have, for example, R group in here, and the other are hydrogens. We could have two R groups, I mean, two alkyl groups, and one of them is hydrogen, and we could have all of the groups to be R. So what we call the three cases in here, we call the first one, which is bonded to one alkyl group, we call it primary carbocation. And the one that is bonded to two R groups, I mean alkyl groups, it's called secondary. And the third one, which is bonded to three alkyl groups, we call it tertiary. And just keep in mind they have differences in their reactivities. For example, like the primary one is the least stable, okay? This one here, the last one is the least stable, and it's reflected on the majority of compounds. The tertiary one is the most stable one. The consequence that comes as a result of their stabilities is the majority. Like, for example, if you have two compounds, one of them will be major, one of them will be minor. What does the R group do? You just notice that the R group, I mean the alkyl groups, are electron releasing groups. And the rule of electron releasing groups, they just make a stabilizing of the positive charge on the carbocation. So the more R groups, the more stabilizing, and that's why the compound will be more. So the electron releasing group, the carbocation, or it stabilizes the positive charge on the carbocation. All right, we are going to explain a point before we go deep to the examples, that the types of alkenes, they could be symmetrical or asymmetrical. The symmetrical one indicates that if you divide it from the double bond, you will end up with identical species. So if you have an alkene and you apply electrophilic addition, you will end up with only one product. But on the other hand, if the alkene is asymmetrical, so you will end up with more than a product. Suppose that I'm adding HBr molecule. All right, so before we start, we have to describe that this reaction represents electrophilic addition in which we have two molecules. One of them is alkene and one of them is electrophile. So HBr works as an electrophile. The driving force for this reaction to take place is the orientation you can see of the HBr molecule. And in addition that the H here is partially positive and the bromine is partially negative, as a result of this, the attack will happen. So one of the carbon atoms on the double bond will be bonded to the hydrogen. So you can see that it's bonded to this hydrogen, and the bond will be broken heterolytically and produce a bromide ion. The hydrogen will be bonded either to this carbon or this. So we have two cases, which means that we have two compounds. So we will have a first compound and the second compound. So we have C and C. Okay, this is CH3, and here we have hydrogen. Here we have the hydrogen. So we're supposed that we have the first hydrogen to be bonded on the first carbon, and as a result of having three bonds, this carbon will have a positive sign, forming a carbocation. On the other hand, we will end up with another compound that looks like this, but in this case the hydrogen is bonded to the other carbon. So we have hydrogen here, and this is the hydrogen that I mentioned earlier, and here we have the two hydrogens and the positive charge for sure. The bromide ion will attack the positively charged carbon, so we can notice that we have to draw the curly arrow that comes out of the lone pair that attacks the carbon ion, the carbon atom, which is the carbocation. And the same story is repeated down below here. We have 1, 2, 3, 4, 5, 6, 7, 8, and we have negative sign. We represent there that comes out of the lone pair just to attack the carbon. So we'll end up with two types or two products. One Okay, we have C. Okay, I just want to do it in a better way. We have CH3, we have hydrogen, we have hydrogen, hydrogen, and just want to draw the other guys that are bonded by red color in order to differentiate. And here we have the same story. We have carbon. All of these guys are, CH3. And here we have, okay, H. We end up with the guys in here. This is a hydrogen. Here is a bromine atom. So we just noticed that since we have asymmetrical alkene, we are having two compounds, like the HBr is added here and the HBr is added here, like what happened. Now my question, which of these compounds is a major in amount? We said based on the stability of carbocations, which of these carbocations is more stable, the first one or the second one? If we come at the first one in here, we just noted that carbocation is bonded to this alkyl group and this alkyl group, which means that the type of carbocation here is secondary, which is more stable. If you look at the other carbocation in here, you can see that the carbocation is bonded only to one alkyl groups and the other guys here are hydrogen. So this one here is a primary carbocation, and which means that this compound with the more stable carbocation is a major. Major compound means it presents in the compound or in the mixture with greater amounts. So this is the major compound, and this one here is the minor. If we want to represent these molecules in skeletal formulas, we have to just draw the propane and just keep in mind the position of the bromine atom. So the bromine atom locates in carbon 2, so the first compound looks like this, and the other compound looks like this, in which the bromine atom is bonded to the terminal carbon atom. So this is the major, and here this is the minor compound. Okay guys, now we're going to take another case in which we have bromine water, and just keep in mind the bromine water represents Br2 dissolved in aqueous solution. It's not the case that we mentioned earlier. We have extra differences, so you have to keep in mind in these. Just think about having this compound 2-methyl bute-2-ene. If it reacts with bromine water, Br2 aqueous, what will be the product? How can I draw it? First of all, you should be able to draw the alkenes once their name is given. So how can I do it? So first of all, we have to draw bute-2-ene, which means we have to draw a series of 4 carbons, all right? And we have a double bond on the second carbon. So this is one, this is the second, and we have methyl group on the second carbon. So it's the same thing. So this is the 2-methyl bute-2-ene. The first step in this reaction looks like the first one we covered before, like Br2, in which we have, like as the Br2 molecule approaches to the double bond, the electrons will repel each other. The first bromine atom becomes partially positive, the other one becomes partially negative, and then the attack starts. So the double bond here, the 2 carbon atoms, one of them will be bonded to the bromine atom. So it could be the right or the left one, and we have hydrolytic fission. Okay, we have a bromide ion in this case. So as we just noticed that the compound here, if we divide it into 2 halves, it's asymmetrical. In other words, we are having 2 possible molecules. So let's draw the first possibility of the first molecules. We have a 1, 2, 3, 4 CH3. Okay, CH, and this one is CH3. Yes, it's bonded to CH3. So in this case, we have one of them is a bromine atom. Here it's Br. Okay, and we have a carbocation. In this case, which is the difference, as we said that the bromine is dissolved in water, we are supposed to have bromine and H2O. So the H2O here, it's represented like OH2. It represents the presence of the lone pair. The lone pair on the oxygen atom in water molecule will attack the carbon. And the same thing is repeated in the other molecule, in which we have the bromine atom to be bonded to the other thing. So we have C, okay, and we have three hydrogens. We have CH3, okay, and here we have hydrogen. Here we have CH3, and the bromine atom, it could be bonded to this carbon. So the other one will be positive. And we have another OH2 that will be bonded to the carbon atom. So this one will attack this. So in your opinion, which of these carbocation is more stable? If we look at the first carbocation, it's secondary. It's bonded to this group alkyl and this alkyl. So this one here is secondary carbocation. This is secondary carbocation. But if we look at the other carbocation in here, we can see that it's bonded to this alkyl group. We have another alkyl group and we have another. So it means that the carbocation down below here is tertiary. And since it's tertiary, then it's stable. And since it's more stable, it has to be the major compound. So let's draw the compounds after combining. By the way, I'm not going to erase anything. I'm just going to put the water like O, H, and H right here. Just keep in mind, once the oxygen makes three bonds, it has to be positively charged in this case. So in order to get rid of this, one of the hydrogen will be leaving the group. So the electrons will go to the oxygen. And you will end up with a hydroxyl group to be like this in here. And the same story is repeated for this compound. This compound will be bonded to OH group. So we have two compounds. One of the groups is bromine atom. One of the groups as OH. And the same thing here is OH and bromine. So this one here, the down below, it will be the major compound because it causes or it makes a carbocation. Here it's minor. If you were asked about like which of these is more stable and or why this compound here is a major compound, you have to mention that it's produced from more stable carbocation, which is tertiary. So it's produced from tertiary carbocation, which is more stable than the secondary carbocation. All right, and you can mention that the alkyl groups are electron releasing groups, and that's why they stabilize the carbocation. So generally, this type of equations they just come frequently in your exam, so you have to think about them well. By the way, guys, the scientist who proposed the story of minor and the major compounds once alkanes react with electrophile, his name is Markovnikov, and he proposed the mechanism of having stable cations like tertiary, secondary, like the story. So this guy is responsible for that. His name is Markovnikov. Familiarize yourself with him.